the Maxwell-Minkert theorem. If F is a flow network G with source S and sink T, then the following are equivalent. F is a maximum flow in G. The residual graph GF contains no augmenting path. The flow equal to capacity of the cut SS dash. Next, let us prove this theorem. We have to show A implies B and B implies C and C implies A. There are the three conditions. If F is a maximum flow in G, there is no residual graph. If F is a maximum flow in G, then there is no more augmenting path in residual graph, and size of the flow equal to capacity of a SS dash cut. First, let us try to prove A implies B. That is, if F is a maximum flow, there is no augmenting paths in residual graph. Suppose F is maximum flow. Assume F is the maximum flow. If there is an augmenting path, we can improve the flow. Okay, if there is an augmenting path in GF, the residual graph, we can improve the flow. That is, F is not the maximum flow. So there is a contradiction. If F is a maximum flow, then there is no augmenting path in GF. Okay, so A implies B. If F is maximum flow, then there is no augmenting path in residual graph. Next, we have to prove B implies C. Condition B is, if there is no augmenting path in GF, then the maximum flow, it will be equal to size of some SS dash cut. Suppose the residual graph GF has no augmenting path. And the set S equal to set of all vertices of V reachable from the source S. and S dash is equal to the set of all vertices V minus S. S dash is the set V minus S, where V is the set of all vertices. Consider the flow network G, source S, then U, V, W, and T. So some edges are coming to T. And we are saying the set S equal to, that is set of vertices reachable from S, S comma U, etc., and S dash, that is set of vertices V minus S, it is T comma V comma W, etc. The flow from S to U is some F1. Let us assume the capacity C1, C2 and C3. This is the original graph and this is the cut. This is the cut, S dash cut. There is a flow from S to U, some flow EF. Then the residual graph will be something like this. Some S2U flow F1, and the residual capacity will be C1 minus F1. Okay, then what about the flow from U to V? We are saying there is no augmenting path in GF. Okay, there is no augmenting path in GF. And what about the flow in this edge U to V? We have said V is unreachable from S in the residual graph. Okay, in the residual graph U is unreachable, sorry, V is unreachable from S. So definitely this edge will not be like this, it is reversed. Okay, then only V is unreachable from S. Then what about the flow? The capacity is fully used. Okay, this edge is exposed. Okay, if there is some flow, there will be a reverse edge and the residual capacity will be C2 minus that flow. Okay, it is not like that. This edge is fully used, then only V is unreachable from S. Okay, if there is a flow, definitely there will be a path, a flow, a edge, reverse edge like this with flow F2, and this edge will be like this with some residual capacity C2 minus F2. It is not like this. Okay, if it was like this, V is reachable from S. We have said V is unreachable from S, so this edge is reversed in residual graph. This edge is reversed means the capacity is fully used. So the flow U comma V is equal to capacity of U comma V. Okay, then we are saying W is unreachable from S, from the source. That means there is no edge in residual graph which will help to reach W from S. If there is a flow from W to U, definitely this edge will occur in residual graph, with flow some F3, and this edge would have a residual capacity C3 minus F3. It is not like that. Okay, W is unreachable from S. If it was like this, W is reachable from S through this edge. Okay, so it is not like that. So this edge will never exist, and there is no flow. Flow will be zero. Flow W to U will be zero. This W belongs to S dash and U belongs to S. Okay. So from this we can reach the conclusion that the edges there are two types of edges coming into the cut and going out of the cut. Okay, in the original graph this edge is going out of this cut. This was the original graph. So edges going out of the cut, on those edges flow will be equal to capacity of those edges. Okay, and edges coming to the cut, flow will be zero. We can say the net flow equal to flow into the cut plus flow going out of the cut. Okay, here we know flow going out of the cut is equal to 0. So net flow will be equal to flow into the cut. What is flow into the cut? It is equal to capacity of the edges. That is the sum of the capacity of those edges. Sum of the capacity of the edges means it is the capacity of the cut. See here, the capacity of the cut is capacity of U, V. So flow will be equal to capacity of a cut. Capacity of an S dash cut. So D implies C. Next we have to prove C implies A. We have to prove C implies A. We have already shown that the flow equal to the flow can be less than or equal to capacity of some S dash cut. The flow can be less than or equal to capacity of S dash cut. Then the maximum value of the flow. Okay, the maximum value of the flow, it will be equal to capacity of some S dash. We know the net flow, it is less than or equal to capacity of some S dash cut. The maximum value of the flow, it can be a value equal to the capacity of S dash, and that flow is the maximum flow. Okay, if the flow is equal to the capacity of this cut, then the flow is maximum. So this C implies A. C is the flow value is equal to the capacity of S dash cut. We have shown that. If F is not the maximum flow, it should be less than some S dash cut. Okay, so that means the flow can be less than or equal to the capacity of some S dash cut. The maximum value of the flow, it can be equal to the capacity of some S dash cut. So C implies A. So we have shown A implies B, B implies C, and C implies A. And the theorem is proved.